I hope everyone's having a good day. Let me just bring up my virtual machine here. And while that's happening, let me kind of review what I'll be doing. I'm recording this on a Friday, and I have several topics to cover, so I'm calling it Random Friday. I'll be talking about indexing and how to create indexes and what they'll do for you, what are the benefits. I'll talk a little bit about constraints and why we might want to use them. Along the way of explaining these two, I'll show you how to use the Postgres explain command and how to find out the database size. I'll talk about JSON in Postgres. So the new, I think it started maybe in 9.2 of Postgres. We're in 9.3. There's some added features of JSON. 9.4 even has more JSON features. This is starting to move Postgres kind of away from a standard SQL database into more of a NoSQL territory. So it's a nice little transition between topics of us moving to the NoSQL in the upcoming weeks. So by now my virtual machine probably is up. So let me get focus on that and SSH into it. And let me change directory. And just let me look at these files I have. So I have movies. All right, so I'll remember those. So let me go into PSQL. Sweet. All right, so let me load that movie database. I think it's about 1 megabyte of, when I downloaded it, it's about 1 megabyte of file. It's not that large of a database. Let's get some information about it. I can actually query and find out what the size is. Here's where I give it the database name, movie. And let's give it a name, full database size. Sounds good. And that's how much it is. So let me just, so we remember, I'm going to copy that. Go back here. Let me just make a original size. All right. That's good. And let's just see how many entries there are. Well, let's take a look at what the tables are here. So we have an actor table, and just out of curiosity, I'll see how many there are in the actor table, how many entries. So not too many, really, 6,000. So it's showing you that it's not a major, a major size table. Let me search for something on that table. It would help to know the structure of the table. Okay, so it has a name field. All right, so let me select everything from actor where, and let me see something pretty, if it's alphabetical, something far down on that list. How about, oops, if I can spell Zoe. I think that's right. Okay, so that's a search. So if we're trying to have a search by name, for example, we know that from earlier computer science classes that even with 5,000 entries, just going through linearly one after another searching for that name is not the right way to go. And if our table was larger, a more realistic size for kind of on-the-job type databases we'll be using, where we might have 1 million entries in a table, definitely linear searching through the database is not the way to go. And fortunately, Postgres does create a binary tree type thing, in a particular instance called a B tree. You can look that up in Wikipedia for details on anything that's a primary key. So here we have actor, primary key is this ID, and we can see it's represented here by a B tree. So it's very fast to search on this ID. let me give you an example, and by that so 5139, let me write this down off line here just so I keep track of it. 5139. All right, and let's see how long it takes to do something. So I can, in order to do that, I can say, hey, explain, analyze, verbose. So that's kind of my prefix for saying how long does it take to do the following. So I can go select splat from actor where name equals. I keep doing the same Zoe error. So that took 0.620 milliseconds. So let me actually stick that search time. Oh, and I already forgot 0.628. That's close enough, probably. 6.2. I screwed up. All right. Let's say I want to search, though, instead on the ID. Let's see if that's faster, because they actually index that with using a B tree. 5139. And you see it's a lot faster, 0.021 versus that 0.6. So indexing here, or at least that's one factor, really helps. So we can create an index on the name field here. Let's do that. So we can just, its syntax is this. So we say create index, and we give the index a name like actor name. And now we give it the table we want, actor, and in parentheses we say what column we want to index, name. So that creates an index. Now let me go up through all my, and just see now what the size is of the database, 9882. Let's see what it was before. So you can see it increases it slightly. So if we had a lot of entries and had lots of columns we were indexing, that might be a disadvantage. But let's now, once we did it, let's see what the new search time is. So we saw the disadvantage. There's our search. That took 0.620 milliseconds. Now it takes 0.061 milliseconds. So it's about 10 times faster. Let me just run that again. That seemed, oops, sorry. So we see it somewhere in the neighborhood of 10 to 20 times faster by indexing this column. So if it's something we're going to be searching on, like name in this actor field, seems like a pretty common sense thing where we'd want to be searching. We don't want to linearly search through that column. That would be a good instance of why we'd want to make an index. Automatically, any part of the primary key is already indexed. So if it's a primary key, you don't need to bother with creating an index, but anything else you might want to. Some things you may never search on, so you wouldn't need to index them. So that was topic number 1. Topic number 2 is about constraints, and let me illustrate that by bringing up a different database. This one is where I'm going to create a table called programmer. Let me actually create a database here first. Employees. All right. And here is where, when I'm inserting stuff into the database, it's going to check that these fields match constraints. Normally what you would want to do is when you're asking for user input in working on a web app, you'd like to check whether that input is valid the closest to the user. So the best approach would be to do it in JavaScript, so even before it goes to the server, you're checking that it's some valid input. Definitely you would check it on the server side, But one option on the server side would just to be do all these checks on within Postgres. It's really a great way, and the benefit is that if you change programming languages or change interfaces, these constraints would still hold. It's all in the Postgres server side. So let's look at some examples here. So I'm creating, I'm going to keep track of programmers I have and what languages they're fluent in. So I have, let's take a look at this table, programmers. So this is nothing exciting. I have an ID, it's serial, it's the primary key. I have the name of the person. I'm just keeping it simple by having one entry for name. It can't be null. And here I'm adding a constraint. And the possibility would be that they can add an empty string, so that would be not null, but it would be an empty string. So we can say we don't want that. The length of a string, the length of a name at least has to be greater than 0. So that's one constraint I'm putting in. The name has to be greater than 0. Here for email, I'm saying it has to be unique, and it has to match this following constraint. Now here, I'm sure you've had regular expressions in some prior class. This is a regular expression. This \a means it's the start of the string. \z means it's the end of the string, so this is going to match the entire string. This \s plus, the \s means any character except white space, so you can have minus the characters A through Z, whatever. It just can't be a space or a tab. So the plus is the cleany plus, so it has to be one or more non-blank characters, followed by an @ sign, followed by more non-blank characters. This is the actual period, followed by a period, followed by more characters that aren't blank. So this would match ron.zaharsky@gmail.com fine, or any valid email address. So those are those two constraints. Let's move on and look at a few others. Here I have a person ID, and so languages, it's a foreign key. It references programmer's ID, so this here. And this says on delete cascade. What that means is that if I delete a programmer from this table, any associated entries in this table will be deleted. So it's a cascade delete is the term. So if I do a delete here, we'll see, I'll show you an example shortly, but everything will be deleted in this table that refers to that deleted person. Language, so this is a computer language like C++ or something. And again, I have a regular expression. So \a, the beginning of the string, \c, the end of the string. So there has to be a bunch of upper and lowercase letters in 0 through 9. You can have a plus like C++, an underscore or a hyphen, and one or more of those characters. Here I just do some insertions just to test this. I insert just some people here with these are all valid ones. I just wanted to start with a little populated. And here I'm inserting, so Ann Hedberg is going to know Python and Java, Clara, Java, C++, and so on. So, all right, let's load that in. Programmers SQL. All right. Oh, I didn't save it, so now I put the programmers in my movie database. Oh well. Sure enough. So there's programmers and languages. Cool. All right, let's take a look at programmers just to make sure that's what it is. And we see all those checks, the constraints and everything there, but it looks like we're good. So nothing exciting search-wise, but let me try to insert some entries here. Let's say I want to insert into programmers. What do I want to insert? How about name, email, values. I don't have a name, and I have some email. ras@umw.edu. It violates constraint, check constraint no name, and no name, if you remember, was the one dealing with, let me just bring that up. The no name constraint was that the length has to be greater than 0. Let's see. Let's try to violate another constraint here. So this is good. Whoops. Let's put in a name. Oop. Fiona's email. Oops, and what did I do wrong here? Oh, I hate. All right, let's try this again here. Fix the syntax errors. I missed a quote. All right, and now that violates the constraint valid email. And the valid email was that you had to have an @ sign and had to have a period. So this is just showing that these constraints are really pretty helpful. Let me try something else here. Let me try to find what programming languages Brian Rice knows. So select, I forgot my table, sorry. And let's just look at the other one for the heck of it. All right, so we have person ID. All right, select languages dot language from languages join programmers on languages dot person ID equals programmers dot ID where name equals Brian Rice. Okay, so Brian Rice here knows Python and JavaScript. And if we looked in that languages table, let me do that. So we see Brian Rice is person ID 5, and let me just prove that to you. Brian Rice is 5, and 5 matches Python and JavaScript. Now let's see if let's delete from programmers where name equals. Okay, so it deletes an entry from, let's just show that it deletes an entry from programmers. Oh, I didn't want to do that. I just wanted to select there. All right, and you see that it deleted it from programmers. Now let's take a look at the languages, and you see there was that cascade effect where it also deleted all the entries associated with Brian Rice from language. It keeps our database nice and consistent, right? We don't want to like delete something, Brian Rice's entry, and still have these languages kind of hanging around for them that we don't know who those languages belong to. So that's kind of cool. I think I explained everything in the table. Let me just check here. Let's see if we can violate the language constraint in when I want to insert a. So let's keep it simple and just add a language for person ID 1. Insert into languages values 1 Python 3. I think that'll fail because I didn't include a space, I believe. So it doesn't match the language format. I would have to do something like that will be accepted. So that was my little blurb on constraints. Constraints are really helpful. It makes the database consistent. It helps just structure everything. So I hope that was a bit helpful. Now I'm moving on to my next topic. Next topic has to do with JSON. And before I start talking about that, I want to just back up and talk about the third normal form. So before the advent of big data, or before things were getting these huge data sets, 3NF was really the way to go. and we've been kind of covering it in the book quite a bit. And it's a good general purpose design, and it supports probably pretty much any, it's kind of query agnostic, that you can do one query or another query. It really doesn't matter. The design has nothing to do with how we're querying the database, or that it's not fine-tuning stuff to one query. But now it's gotten to be one schema out of many possible ones. So if the goal is to have an interactive shopping site, we might want to go with this 3NF design. But if we have a huge amount of data that we're trying to sift through to analyze shopping patterns or something, that's where these other ones like a star schema or a snowflake schema come in. That they're more used in when we're not these necessarily interactive approaches, but when we're trying to do data analysis. The problem with 3NF is that when we're trying to do huge joins on all these multiple tables, and we've seen even with very minimal queries that we're trying to do, involves many multiple tables. So for example, we're trying to find what actors are in what movies. Already we're using 3 tables. We need to do joins from all these tables. These joins get very complex and are time-wise. So there are these other schemas. So we're moving away, when talking about Postgres supporting JSON, we're moving away from 3NF. What we're designing is no longer 3NF, but we may be willing to give that up because of the nice features JSON has. JSON stands for JavaScript Object Notation, and it's a form that's really easy for humans to read and write, and it's easy for machines to do the same. So here's an example. It just looks like a Python dictionary. So if you think Python dictionary, you're good to go with this JSON stuff, right? So there's some key, which is necessarily a string, and each key has some value. In this case, the value is just another string, I guess, but it could be other things as well. So Postgres, since version 9.2, allows us to have this JSON data type. And let me just bring that up right quick. That's not the one I want. Here we go. So it's a database of having to do with publications. So I have just some ID for primary key, and I kind of did 50-50, I guess, on whether it's third normal form and how much I'm sticking in this JSON. But this idea is that there's a person and they have a publication, and this publication could be a lot of things. It could be a book, it could be a journal article, it could be a conference proceedings, and depending on what those are, there might be different attributes for each. So for example, here I have Ann Mulkern doing a conference proceedings. There's a title, and then I have, well, what conference was it? When was the date of the conference? Then I have Polly here who did a book. There's the title of the book. Books have publishers, so I list the publisher. Journals, there's a journal article. There's the name of the journal. There's a volume number associated with the journal, and so on. This is just a simplified example, but showing for different things, we have different structures. So this wouldn't fit quite well into, one table, at least, that if we wanted to do 3NF, it would require kind of multiple things to do. So here I'm kind of scrunching everything using this JSON data type that Postgres allows. So let me go into my Postgres here, and let me make sure I create a database with that one, since the horrendous error I made the last time. Yes, I do. Okay. I think it was called public. All right, this is a fairly small one. Let me, so I have publications here, which what I said before, where I showed before, with first name, last name, year, and JSON. So now let me search for something. Let me find the titles of all journal or all books in the database. So the syntax is the pub is the JSON column. Then within that JSON itself, let me bring that up again. So pub is here, And I want to find all the thing. This is the pub column, that whole JSON, which I'm just doing a horrendous job scrolling. So it starts here. And I want to find all those occurrences with type book. So pub title from, what do I call it? Publications, where pub, again, pub is the column, and then I can go within that JSON object and grab a particular entry, a key. So I'm putting in a key here, type equals book. So there were two books. One is The Structure of Japanese Conversation Invitation Strategies, and Conflict in Harmonious Japan, Myths and Evidence from Conversational Interactions. So I can find the publisher. Let's see, I don't remember that key. I think it might be just called publisher. Yes, it is. So let's get the book and the publisher. That should be an easy difference. Pub and I kind of ran out of room here because the columns were sort of large, but I got the two. All right. Let's say I want all the journal articles. Let's stick with books. All the books written, I guess they're both written by Polly Zatrowski. Let me find something that's more interesting here. Let me do the illegal, I'm God and I know everything in the database type thing. Okay, so there's a journal and there's a journal. Sure, so let's find all the journal articles Ann Mulkern wrote. Let's kind of combine, sorry. So I'm just, let's say I'm interested in the title, and I'm interested in the journal it is, from publications, where pub type equals journal and first name equals Ann and last name equals Mulkern. Okay, and oops, I didn't get the journal on that one. Oh, JName. I'm sorry. I don't know my JName. All right, let's give that another shot. Here we are. And so we get the answer here, but we see that we have these funky column things, and maybe we actually want a column named something more reasonable than just this question mark column. And this is true with any select statement, not just these. So let me do that. So I can go as journal, so that column will be titled journal. And that will be called, I think I just misspelled journal, didn't I? Okay, that title will be called title, or that column will be called. So that's how I would get the columns to be actually called something. This is true with anything, so let me just show that. Let's switch back to some other database here right quick. Let's go movie. Yeah, sure, why not? Okay, so oop, I did the same thing twice. All right, so instead of name here, let's say I want to show all the actors whose name starts with Z, but I don't want to name the column. Well, I'll show you the difference here. So let's just select name from actor where name like. Okay, so the column is named name here. But I can change that column name to be something like actor. And that changes it there. Sometimes that's useful when we have multiple names. Like if we have, I think maybe in the city and country databases, we have both columns named name. It'd be weird to list the city and the country and both have them be name. Let me just take a look at that right quick. Oop, I never loaded. Let me load. I think that's what. Sweet. Oh, that's dumb MS. All right, so let's take a look at city here. So it has a name, and let's take a look at country. Maybe I'm wrong. And country has a name as well. So we wouldn't want two columns. Let's say we want to find all the cities in Canada. Let's see if we can do that query. Okay, so we want to select city dot name, and let's say I want to say they're from Canada. Country dot name from city join country. This is where I should have been paying attention to my design here. So city is called country code. Join country on city country code equals country dot code, where country dot name equals cam. So there's all the cities in Canada, but notice these column names are both name. That's sort of ugly looking if we're printing it for our boss. So we can fix that with that as command. Sorry, I'm scrolling backwards here. So I can name the country name. I'll just call that country. And I'll call this city. Now I have the columns named city and country. The other thing I want to show, since we're on this topic, and it'll probably be the last one for today's Chaotic Friday episode, is this as is optional. So it could just be that. Select city.name city. So there's kind of an implied as there. Country.name country. And I get the same result. City, country. So I think I should stop. I've shown you how to do indexes on various columns, how to create constraints. These are very useful to do. And I've showed you JSON, and I've given you a few other hints along the way, how to analyze queries, how to determine the size of the database, and now how to rename columns. So I'm hoping all this is helpful, and you'll use it in your upcoming projects and throughout your life as a web app developer. Thanks. Bye.